the description of the stochastic dynamics in a high-dimensional space. So basically, we had this intuitive picture that if you have a rugged energy landscape, your stochastic trajectories may not freely diffuse through the surface or through your configuration space, but rather would spend an exponentially long time in certain regions that we identify with the basins, or also called states, and then perform quick transition among them. And okay, this observation was the key to start to sort of foresee the need of coarse graining the dynamics in order to establish, if you want, equivalent classes between stochastic processes. Stated differently, any stochastic trajectory will be by definition different from one another, but some stochastic process some trajectories may describe the same stochastic process. For instance, the black and the orange trajectories in this particular sketch represent an event in which these four states, let me label 1, 2, 3, and 4, are visited in a specific order. However, on the same energy landscape, under the same dynamics, because of the energy fluctuations, different processes could be realized, such as one in which, I don't know, you first go from 1 to 3 and then go back to 2 and then from 2 to 4, not necessarily with the same probability. So the idea that we were trying to pursue during the last lectures was to go from a microscopic configuration state descriptions to a coarse-grained one in which my relevant degrees of freedom are the instant populations or of each of these states. This is the eth state, so the population of the eth state at MT, or equivalently, because of the frequentistic interpretation of probability, if you want, the probability to find a system in any of these states. So you can always have this idea of either you imagine your system to be made by many equivalent copies, propagating independently in the same energy surface, and therefore you can associate a population to each state at any given time t, or you can take a slightly different point of view in which you have only one copy of your system, and basically instead of talking about population talk, you describe your dynamics in terms of probability that your system ends up in one of the states at a given time. And the idea was that it is actually possible to perform such a coarse graining of the dynamics by relying on the connection. Basically, the essential idea was that of describing the probability to be in one state in terms of integrals over configurations with characteristic functions. And the characteristic functions were able to select the eth state. So this is the Fokker-Planck probability. And for instance, you can write this in terms of some initial configuration probability defines over initial distribution. And the initial distribution could be, once again, a sum over states and corresponding initial distribution. So that basically you're neglecting the probability of finding a particle outside in the cold air by going from this home to this home or from any of the states. And this is okay as long as these are rare events. And therefore, even in the equilibrium, the probability of observing the system in the intermediate region between the states is exponentially small compared to the probability of finding a system in any of the states. And therefore, these descriptions, of course, is correct up to exponentially small corrections. So there's an intrinsic time resolution, but also an intrinsic, if you want, energy or space resolution within this approach. And everything is connected by the fact that during the stochastic dynamics, you change space, but also you change, you change space in time. So this is the reason why ultimately you get connected. So we discussed that this was a sort of renormalization group transformation going from a Markovian process in some very large dimensional space with a dense set of variables onto a Markovian process on a much lower dimensional space characterized by a discrete set of degrees of freedom, they call the populations. And the new equations describing the population dynamics in this Markovian limit could be written as a so-called rate equation. There is an equivalent form in terms of finite displacement, which involves the transition matrix rather than the rate matrix, but the basic idea is the same. And then once you have achieved this, then of course you can look at your system's dynamics, retaining only the degree of information that you've chosen to be relevant. And how do you choose what degrees of information you think are relevant? By selecting appropriately the lag time delta t, because the delta t time sets basically the minimum time interval that you're really interested in resolving. Now, even after these steps, suppose you choose a very short delta t, and then you end up with, I don't know, typically 10 to the 4 states. We're considering a prototypical complex system such as, I don't know, macromolecules, proteins, or a DNA. And then you have a network. Your dynamics is now represented by a connected network with vertices representing the states and edges representing directed edges representing the transition matrix or the rate matrix, depending which formulation you use. Okay, so this is a network representation, and you can even represent it graphically. For instance, some people do that by putting larger arrows when you have a larger rate of transition, and maybe weaker arrows when you have a smaller rate of transitions. So your network becomes illustrative, and by following, for instance, by following the largest rate, you get an insight, just to give you an idea, of the maximum flux transition. So basically, you get an insight of where you have the largest amount of processes flowing. And in an analogy, if you were to do the same with, if you assume that the motion of cars is a Brownian motion, which is true only in certain cities, but let's say if you've been to Tangier in Morocco probably, or in any Indian city, this is a fairly good model. If you go to Zurich, probably it's not. But anyway, assuming for the sake of argument that, say, cars move according to Brownian motion, then you would have that, the maximum flux of cars that start from Trento and end up in Rome, they will form a network. And you probably would guess that, the maximum flux goes through Bologna, Venice, Bologna, Florence, and Rome. I don't know, along the A1 highway. So you see, being able to identify fluxes and discretize the dynamics at the level of Markov states immediately bears insight into how phenomena occurs. However, it might well be that your representation is still too much detailed, and maybe there are so many nearly independent transitions in your network. But these states are all very close structurally or kinetically. So sometimes you want to perform further reductions and further lowering even further the resolution of your system. And this is a problem that normally goes under the name of clustering in network dynamics. Well, in the statistical mechanicals language, this is called clustering of microstates or states. In the more information technology language, this is more called clustering of nodes in graphs. But the idea is that of understanding that some of these dynamics that connect states is faster than the other. So for instance, I could give you a simple example. Suppose you have a network made by, say, some points here with a very, very fast interconnection between them. And I will just draw a few of them, not be drawing all of them, because otherwise I spend my day drawing. And then I have another bunch of people here, a bunch of states that are fast interconnected. And maybe in between the two, there is a barrier, and you necessarily have to go to a weak, very weak transition between these two states. Now, under this condition, I think we would all agree that at a low resolution level, we could identify this region with one macro state and this region with another macro state. And that's, there are countless examples like this in science, and even in history, in geopolitics. After all, if you look at the evolution of states from the 16th century to today, I'm talking about nations. They basically follow the need of clustering because of the network representing the economy. If you look at Italy in the 1600s, it was a bunch of states. Now I'm not going to draw Italy very carefully, but there was the Vatican State. There was well, that's the worst painting of Italy I've ever seen. So let me draw it as I should draw, as my kid draws Italy, right? That's very bad, but never mind. So you would have, I don't know, here, then I guess here and here. And the reason you had this clustering is because the economy was basically traveling fast, needed to travel fast on this scale, if you want to think about that in terms of, I don't know, economy-based picture of history. And as the market was increasing, the need came across to have a larger network for fast interconnection of goods. That led to the 1900 to the formation of the countries as we know it today: Italy, Germany, France, and they all basically occur in the same historical period. And that's shortly after, the Industrial Revolution, which created the need of a market and the need of propagating the goods. And then if you propagate even further, then you go into the macro states, United States, Europe, federations of states in Russia. And all of this can be viewed as an application to politics of the same idea of clustering due to some need of having faster kinetics be favored with respect to slow kinetics. Now, the clustering problem is a central problem in information technology, but from the point of view of a physicist, this is nothing but renormalization group, because all you want to do is to lower the resolution of your descriptions and identify states and compute rates between macro states based on renormalization group flow. And in fact, I must say, in 2000, I guess was 18, together with my students, Orioli was a master student at the time, we worked out the renormalization group flow of the master equation and showed that it actually generates clustering of states and allows you to identify to which macro state a given microstate can be assigned to and compute the rates. And everything within the language of renormalization group theory, which is the natural language for this type of approach, even though chemists and computer scientists usually don't know it because they come from a different background. And so this is an example of how sometimes some specific background of a physicist can be applied to a different field where this idea, for instance, of variable resolution and exploitation of the gap was not so formalized. Okay, so that much for the, one could go on forever discussing on Markov state models. They are a very active field of research today. And they are now, this kind of investigation is now pairing up with a revolution in statistical computing and in machine learning, to a point that now the two fields are merging in a way that I will try to give you some illustration in the next few lectures. So in view of the revolution that there is really taking place as we speak, basically, I decided since a couple of years and to progressively enlarge this part of the course to give the students, equip the students with tools that I think will be key for the science of tomorrow, not just for the science of yesterday. So the next logical step in this course will be a very, very brief but math extensive, I must say, introduction to the field of statistical computing. Now, what is the statistical computing revolution? Many people say we are experiencing an artificial intelligence revolution, but I don't agree, and many people don't agree. Most of the algorithm in artificial intelligence and neural network that we use today were available 20 years ago. Maybe computers weren't good enough. Maybe some particular features such as the back propagations were limiting factors. But was really, but not, no big revolution, no new paradigms being proposed in artificial intelligence. Things are getting understood better, of course, but there is no such a thing as a paradigmatic revolution. On the other hand, there is a paradigmatic revolution in our understanding of large data. So this is the big data, if you want, challenge. This statistical computing is, if you want, a corner of a larger buzzword called big data. And in some sense, the problem that we are trying to face is a big data problem. So once again, let's go back to the situations that is familiar to a physicist, which is one in which we have a molecular process we want to study. We run a very long molecular dynamic simulations, Langevin simulation, whatever you want. And in the end of the day, we have a large ergodic trajectory or a huge collection of short non-ergodic trajectories, like in the folding atom process. And now you've simulated the system, and according to some prescriptions you have decided beforehand, you sort of agree that you have reached convergence, and that from the computational point of view, you've done your job. But then a big question comes, and the question is, so what? So how do I make sense of that large data? What do I learn from it? There is more information that I can possibly process with a human mind. When information is larger than the one that I can process on a human life scale, there's clearly some problem that I need to face in order to extract information from the data. And the Markov state model is in principle a way of making sense of a huge amount of larger data, scaling down to a simpler representation that retains the relevant information, not because I cannot do it without it, but which is probably also the case, not because I cannot simulate the system without this, but because I cannot understand the simulations without this. Okay? So in the last lectures, we discussed that after you've done it, you can get something. But the question is now that I would like to discuss with you, how do I go from microscopic simulation data to a Markov state model. How do I build a Markov state model? Okay, this looks like a very boring problem. It is one of the most fertile problems for applied mathematics of the last decades, and is home to beautiful mathematics, as I will show. I mean, I must say, I never was able to get out of the spell of mathematics as a theoretician. I mean, I continuously force myself to look at the relevant experimental, phenomenologically relevant, to keep my eyes on phenomenology, but there's nothing I can do. I was born as a half mathematician somehow. And when I see beautiful mathematics, I can sort of appreciate the aesthetics of it, or I think I can, and I fell in love, and I fall in love with the aesthetics of and the elegance of mathematics. And I think there is quite an amount of elegance in the development of statistical computing and the mathematics of it that is going on, as I will try to give you a glance of. So why is it building a Markov state model difficult? After all, we already gave a prescription, right? So we look at the trajectory. When the trajectory spends a lot of time in a point, well, we assign that region with the Markov state, and then when the trajectory spends some other time in a point, we associate this with another Markov state, and maybe we do this starting from many points. When we see dark spots, we have microstates, and from the rate of transition between the rates from the stops, from these stations, so to say, I can build a kinetic matrix. Fine, this is all nice in 2D. Already finding spots in 3D is more challenging. Now think about 10 to the 5D. As soon as you move out and your system becomes high dimensional, you immediately face a number of problems that are shaping the system in a way that makes it very far in properties from the low dimensional pictures we can draw on a piece of paper. First of all, when you have a data set of endpoints in a d-dimensional system, the distance between 2 points, any 2 points, say the nearest neighbor points, well, this is obviously even the Euclidean distance. Let me even the Euclidean distance for simplicity. But then clearly this object goes to infinity when d goes to infinity. So in a large dimensional space, distances blow up. And you can show that, in fact, any data set becomes sparse, arbitrarily sparse in infinite dimension. What is a sparse database? Data set is a data set in which, so what we would like to represent the dynamics would be like, my configuration look like this if I project it on a plane, for instance. Okay, I am not populating the entire space, but I have enough statistics to understand where the states are, say. So it is sparse because I don't populate the entire place, but at least I see regions. And here, for instance, and here, the system is not sparse. But at infinite dimension, at least in terms of scaling, your data set always look like this. With this distance becoming infinite, a divergent parameter. And if you want to associate density, for instance, you know, a way to visualize this is, how do I understand where the states are? Well, I have my plane, I build a grid or a lattice, and I simply count how many times a configuration falls into one of these beats. But you know, if my system is characterized by this intrinsic time scale A, then typically A must be much smaller than the size. So you need a certain number L of intervals or cells for each dimension. And then, of course, in the end, how many cells will I have? I will have L to the number of dimension for a cubic one. So that's typically L to the 10 to the 5. Now, clearly, in each of these cells, you have to have enough data to populate a statistic. So let me say at least 10 data points. It's the very least, right? So let's say 10. So can you ever produce a data set with so many points? Clearly not, right? So this is sometimes called the curse of dimensionality. And hey, that's the sign of a global era. So understanding large data, and in this case, understanding molecular simulation as a paradigmatic example of large data, not necessarily as everything we might be interested in, is essentially fighting the curse of dimensionality. So is it a fight we can possibly win? And when is it that I have a chance to win it? Now, it looks like an impossible. So, if this was really the case, even performing a molecular simulation, say, of a system consisting of 10 atoms, I mean, really, are you kidding me? 10 atoms is half of an amino acid. A single amino acid is typically 20 atoms. Okay, so even the smallest uninteresting piece of object will have a dimensionality. Say, I would have a dimensionality 3 times 10. And then, of course, say I want to have a box of at least 1 nanometer. Wow, that's really, let's say 2 nanometers. And a spacing of 1 angstrom. That's L equal 20. And therefore, it's something like 20 to the 30 cells to cover configuration space. Of course, you never, ever, ever, ever will be able to be ergodic and cover all the cells. But physicists know this since the 40s, right? And the answer the physicists developed during the Manhattan Project, actually, to fight with this problem is called importance sampling. So what Monte Carlo does is precisely to address this problem. It says, I don't need to be exhaustive because most of these cells will be empty anyway. My systems only visit certain configurations in certain conditions. And if I can access only the region where the probability of finding the system is large, then I'm happy. Now, importance sampling or stochastic sampling was a pivotal concept in the computational physics that shaped the science of the 20th century. Now we are looking now at a slightly different problem, which of course is related with importance sampling, but has nothing to do with sampling. And it's the problem of reducing the data, understanding the data. But clearly the notion of importance sort of must remain. So let's go back to our case. So we had a couple of states. Now suppose that my data look like this. Now what this picture is telling me is that at any finite statistics, if there are regions of high probability and low probability, the effective dimensionality of my system is not that of configuration space, but of the relevant curved manifold called the intrinsic manifold, where data tend to agglomerate, right? So if I could project my data onto some relevant low dimensional space, possibly this could be a nonlinear space, a differentiable manifold. Or it could be a linear space, but the mapping could be nonlinear, which is basically the same thing. That's what you do. I don't know if you have done some differential geometry or if you've done some general relativity, which is basically the same thing. And you define a local system of coordinates, and it's a highly nonlinear mapping that takes you onto the local coordinates. The local system of coordinates, of course, is a linear space, but it lives on a nonlinear manifold. So the identification of a local reference frame in general relativity is where all the dynamics is actually buried, right? Because it has to do with the curvature of space and the manifold and blah, blah, blah. Have some of you taken general relativity?
Yes.
Okay, so
Yes.
you will recognize some of these analogies. I will, of course, assume no general relativity for this course, of course. But I just want to say that's a place where understanding differential geometry can be of help. But let's go on. So the concept of importance in a framework of stochastic processes on a large dimensional space goes hand in hand with the idea of dimensionality reduction. So really, if the curse is due to the dimensionality, the remedy is to lower the dimensionality as trivial as it may sound. And how much should I lower the dimensionality? Well, as much as possible, but not a bit more. And if I was to give the proper theoretical physicist answer is, well, there is a very, very last point where I can lower dimensionality to. And it is until I've passed the last gap in the spectrum of my Fokker-Planck operator, right? I cannot, if my Fokker-Planck operator has a bunch of gaps, at some point there will be the one next to the closest to the ground state, and I cannot lower the dimensionality lower than this, right? There's nothing I can do more than that. But nature is often more perverse than we hope, and quite often we end up being in a situation where we do things that we wouldn't like to do, but we have to, and sometimes we have to make compromises with the devil. And we'll see when this happens in real life. But at the moment, let's not worry about this and try to set up the system. So how do we perform dimensionality reduction? And in the following few lectures, I will discuss about dimensionality reduction. And I will basically use follow two main avenues. And I'd like to split the methods or the techniques that become useful to perform dimensionality reductions into two main families of categories: spectral methods and geometrical methods. Spectral methods are all based basically in estimating eigenstates left or right, typically left, of the Fokker-Planck operators. And they basically follow the idea that the relevant dynamics is the one next are the lowest ones. Geometrical methods are instead based on trying to use differential geometry mixed with statistics in order to identify the relevant manifold, for example, based on following regions of high density in configuration space to identify an effective curved manifold representing the data. And then looking at density on this manifold to reproduce the data. So you see, the advantage of spectral methods is that they have intrinsic dynamics inside, they have dynamical information. The disadvantage of spectral methods is that they have dynamical information, meaning that you need dynamical information. But sometimes the way you get the data is by, so to say, half cheating. You cannot really do it by integrating the equation motion. Perhaps you have to use other methods. Perhaps this method violates certain properties such as microscopic reversibility or whatever, because in order to enhance the sampling, you're ready to compromise with the devil. So you cannot really rely on the spectrum in order to gain information, but you can still rely on concepts like proximity and density on a curved manifold. And so people can rely on geometrical methods. And once again, these concepts are so general that they are applicable beyond physics, basically to any complex system you can think of. So what I will be doing today is begin discussing some concepts in spectral methods, and I will upload improved versions of the lectures that I'm working on. So anytime I finish a lecture, I'll make sure that the notes will be up to date till the subject of the latest lecture. But if you jump ahead and try to read more, you do it at your own risk, because I'm still working on whatever will come next. Because like I said, this idea of switching the course towards and gearing it towards these concepts is a fairly recent decision I've made following the revolution in statistical computing. So the notes on polymer physics have been there for almost a decade now. They're quite safe, and I don't need to work on them. I don't even need to read them before the lecture, to be honest with you. While I'm in an earlier stage of development of this, so things are still work in progress. Okay, so let's move on. So I'd like to spend the next 45 minutes introducing the pivotal concept in spectral methods. But I'd like to do that after a short break, because I don't want to bore you. And I need your mind to be relatively fresh, because there's going to be a little bit of mathematics involved, which for some of you is piece of cake, some others not. So let's take a 5 minutes break, and let's gather up here at, say, 5 minutes. It's like, no, let's make it comfortable. Let's say 5:20, okay? I will start sharp, so don't be late. Okay, I'm starting back. So let me begin. And let me begin by discussing the need for relying on spectral information when trying to perform clustering of points, identify, for instance, the Markov states. And it's the way that I find most approachable and is to start from the vanilla 1.1 idea that everybody would have and show why it doesn't work, and then move forward and see how spectral information can solve that problem. Okay, so suppose we live in a multidimensional space and we want to use um, how do you say, an algorithm to identify the Markov states that doesn't rely on me looking at a piece of paper, because the paper only holds in 2 dimensions. Okay, so the very naive way of moving forward in this quest would be, we would reflect what we do with our eyes, right? So what do we do here in 2 dimensions? We say, okay, I see that in some regions points are very close to one another, and in other regions points are very close to one another, and then there are regions where points are very far from one another. Okay, so maybe I want to associate points, right? I want to use basically a distance measure and cluster according to relative distance of points, assuming that they are those. If you are in a state, you're close to one another. But there are still algorithms that do that, although I guess you begin to realize this approach is very intuitive as the eyes goes, but it may not be the most physically sound. And it's very simple to provide you with a counter example that explains you a situation where such an approach would fail badly. And for instance, let me do that. For instance, suppose we have a one-dimensional system, but with a non-periodic energy barrier, meaning, for instance, that my energy barrier, first of all, is not degenerate in energies, but also some states have a larger entropy and some other have a smaller entropy. Now take these 2 states here. Suppose this is my temperature. Okay, so I should assign to the same states all the points that are within this temperature. So let's take this point and this point. So let me call it point 1, point 2, and let me draw point 3 here. Now, clearly, if I assign exclusively based on a distance criteria, my algorithm would assign point 2 and point 3 to one state and point 1 to another, maybe. Because the distance between point 1 and point 2 is larger than the distance between point 2 and point 3. However, it takes no time for a scientist to understand that this is not correct, because what immediately our brain does is, well, this cannot be true, because if I let this particle evolve, then it will immediately go somewhere here, and so will this one, and these points will be close to one another. While this point will only very rarely go to the other states because it has to overcome a barrier. So you see, what our brain instinctively processes is a projection of the future dynamics, understand the likely outcome of the dynamics, and categorize the configuration on the basis of what is likely to be happening in the future to distinguish the states. Okay? So let's do this in mathematical terms.
Let's translate this very intuitive idea in mathematics using the concepts of stochastic dynamics that we have described. So this brings me to the definition of a norm between two configurations, 2 points in configuration space. And we will call this the diffusion distance. Diffusion or diffusive or kinetic sometimes distance. And how is this distance defined? Well, it is basically exactly what we've done. So let me build it by hand and I say, okay, if I start from my configuration X and I run a T-long molecular dynamics, I will generate a probability distribution, which I write this way. Sorry, let's go into Z, because Y is already taken by the other point. Now, if I do the same starting from another position, the probability of ending up in Z may be slightly different because of the initial condition. Okay? So an interesting concept to look at is the distance between these two. Okay, let me draw this in a form that is not okay, too much crowded on the board. So. Now, of course, this depends on Z, and I'm not interested in Z. So let's imagine for a moment what will happen if I am in the same basin. I start from a delta function distribution, probability focused in X. I start from a delta function distribution, probability focused in Y. And then I let the system evolve for a time tau. Now, if tau is of the order of the local relaxation time, right? Let me use a different color for this. After some time t, this will have evolved into a Boltzmann distribution here. And this will have evolved to the same local distribution time. If my time is much larger than the local relaxation time, yet shorter than the global relaxation time. So these two probability will basically be locally Gibbsians. So I integrate over the final position, but since I'm not interested in the Gibbsian character, the fact that they are Gibbsians, the fact that these are e to the minus beta u doesn't really matter. The important thing is that they converge to the same distribution. Let me divide away by the Gibbs measure. So pi of x, pi of z is precisely my Gibbs measure. So if I choose tau properly, this definition of norm will, in fact, satisfy important the intuitive properties that the distance that these 2 points belonging to the same basin will converge to, will be defined to have a small diffusion distance. Now, to be honest with you, I'm not sure that this is really a norm in the sense of metric spaces, because it certainly is positive definite. It certainly is satisfying the property distance between x and y is equal to distance between y and x. I'm not sure about the triangular inequality. I have never processed that, and I don't think this is particularly relevant because you don't have to build a metric space out of this. But just to say that the word distance, I have to check whether it is really a norm in the sense of metric spaces. Okay. But for all practical purposes, this doesn't matter. It does what it does. It tells you how far you are from Gibbs. What is the relative distance from a Gibbs distribution locally starting? Clearly, if I start here, I will converge to a locally different Gibbs distribution, and this norm will remain large unless I choose tau to be large enough that this interconnection becomes visited many times during the dynamics. So the notion of time resolution now enters in the definition of distance. And tau, the lag time, begins to be part of the game. And ideally now I would like to associate to the same cluster states that have relatively short diffusion distance. And so let's dig a little bit further into this concept of diffusive distance. Well, let me use the spectral representation of my propagators. Let me use the spectral representation of the propagator. Now you begin to see how the spectral information becomes important, right? And if I do that, of course, now I have 4 terms. Let me see what is the result. But I think I will only do some of them because you see how the calculation goes, and you can do the rest yourself, okay? So I open a square bracket that eventually will have a power to the 1/2. I will write an integral in dz. I will have my Boltzmann weight sitting here ready to be used. And then now I will split this into sum over n, right n z, left n x. And now, for instance, I have this term square, I have this term square, and I have negative of cross product twice, okay? So let me look at the first term, this term square, okay? So if I want to evaluate this, I will put the sum over m, right m, z, left m, again x, and again e to the negative mt. Y is still X because this is Y, of course, because I'm looking at this term squared. Now, there will be other terms here. There will be a square of this, and then there will be this to the 1/2. And I will not bother with the other terms for now. Okay? So let's focus on this first term. Now, the crucial observation is that if I take the right eigenstates and I divide by the Boltzmann factor that sits there, I get the left states, right? We've been discussing this property that basically is an implication of the detail balance condition. So this is basically due to detail balance. Why do I say that? Because it's because of detail balance that I can turn Fokker-Planck equation into an effective Schrodinger equation. And this non-unitary transformation basically is deeply rooted into the connection between left eigenmodes and right eigenmodes of the Fokker-Planck operator. Okay, so rather than writing this, what I can do is to multiply these two, I get the left. But now you see what happens. I get a nice left-right integral, and that's the only part that depends on z. So now I can do the integral dz, right n of z, left n of z, and I know that this is going to be delta n of m. So what this part has given out as a result is left, I have a single sum now. I have a left n of x squared, and I have e to the negative 2 lambda n tau. Now, if you do the same with the second term, so you have square cross term, right, in the product. Now the first square is this. The second square term, now I'm going to fill up these spots. I get a left, but in y. And again, a negative of x and y. If you do all the others. I mean, it's completely trivial to work out the others. But now this expression can be rewritten in the following very, very illuminative way, enlightening way. So if I call L tilde the left eigenstates multiplied by their exponential factor. I can absorb them into it. I discovered, so let's say L tilde n of x is e to the negative lambda n tau n of x. I've discovered that the diffusion distance is a Euclidean distance in this space of coordinates. I've identified a mapping, a highly nonlinear mapping that defines a local coordinate frame. Because my metric is Euclidean in the space of the Ln coordinates. So in other words, I've established a mapping that goes from x to, which has 3n coordinates, right? To Ln of x, which in principle has infinitely many states, but only those that are within the inverse lag time are relevant here. So I have a fixed number of states. And in, if there's a gap, then this exponential factor simply goes away, because all the frequencies below the gap, the exponential factor is basically 0. And all the frequency, so it's 1. And all the frequencies above the gap is essentially 0. Right? So this gap basically can be used as a filter for the m states if there is a gap. If there is no such a gap, then you have to worry about this. And let's be general, in which case the gap is probably too weak to be exploited. So in which case you really have to retain the tilde here. But the point that I want to say is that we have discovered a nonlinear mapping such that after this mapping, my dynamics in this virtual plane defined by coordinates L1 and M is Euclidean. The Euclidean norm in this space is the diffusion map, is the diffusive distance in the original space. So the left eigenmodes of the Fokker-Planck operator have an important geometrical and role. They are an Euclidean local reference frame in which the metric is Euclidean, even though the underlying dynamics even if I'm interested in the concept of distance that is as far as possible from the trivial Euclidean distance. So if I can compute the left eigenmodes or at least estimate the left eigenmodes of the Fokker-Planck operators, then I have a way to say what should be grouped together. Because I have a way to understand the things that are close in this space are closed genetically. So going back to our example, now I cannot do it in one dimension, because in one dimension, the mapping is not very, in one dimension there is at least one trivial left eigenmode that is the identity, if you remember. And then I'm not actually projecting, I'm embedding, because if I take the second, the projected space is larger than the original space, right? So really, it is impossible to do a one-dimensional analysis. So let me go straight to a multidimensional case. Suppose I have a point scattered in a two-dimensional potential. But maybe the potential is weird enough that, I have my points, but I don't really know where they can diffuse to. So the Euclidean distance of these points may not be a good representation. Maybe because one of the two states is skewed, for instance, like in the other case, and the other one is broad. I don't know. So maybe in this plane is difficult in this representation. This is the Euclidean representation to identify Markov states. Now suppose that using some God-given methods, and we will have to supply for that later on in this course, I'm able to give you, say, the first two non-trivial, let alone this is trivial, but I have a good representation of these functions. Now, instead of plotting in the XY plane, now let me plot in the values of this function. How do I do? Well, I take my point in my data set, say the first point, x1. I evaluate L1 of x1 and L2 of x1, and this will be a coordinate in this plane, say here. And then I'll do the same for L2, x2, x3, x4, x5. Now in this plane, my points will look like this. And so I will be able to say, fine, here's a state. Here I can define a simple geometrical criterion and associate the stars. I want to appreciate that I'm using the plot for visualization purposes, but the code can be written without having to draw things, because my code would ideally contain a subroutine that will evaluate the eigenfunctions, the left eigenvalues. Okay? So these concepts of spectral representation of the Fokker-Planck operator ultimately are powerful enough to yield a very strong, to solve a very complex problem, that of understanding what establishing equivalent classes in systems where purely geometrical considerations cannot. Obviously, somewhere the challenge must hide. And of course, the challenge is, yeah, right. But hey, you have asked to solve the Fokker-Planck equation in 3n dimensional space to get these points, right? These functions. This is a really hard problem. I mean, have you ever thought about solving Schrödinger equation for 10 to the 5 distinguishable particles? Even for 100 is a non-trivial problem, right? Well, it turns out that there are excellent approximation methods for doing that. And in the next lectures, I will introduce schemes that have been developed, again, very recently, last 10 to 15 years, to perform this mapping and to perform this projections, ultimately leading to the concept of diffusion map. Because what you see here is in fact a diffusion map, a map in which you gather together things that can diffuse fast into one another. Okay? Are there questions so far? Questions about last lectures you would like to discuss in the remaining 10 minutes? I will not start the next section of the course now because there's no point to start a new chapter, new session with 10 minutes. So I'd rather spend these 10 minutes to discuss questions with you if you have any. I received an email from some of you, some of which I replied, some other I couldn't. So if you have questions, this is a good time.
I
Maybe
would like
just-
to point out, okay, go ahead, please.
No, you can go first.
You first, please.
All right.
Okay, thank you. Just about the coefficient, when we were writing the Markov states Ni,
Yes.
and we had the coefficients Cn
Yes.
when expanding on.
Yes.
Okay, and that coefficients that are defined as the integral in the x of left eigenstate times the probability of x and t. Is that the initial time?
Okay, so the best thing is I go straight to the point in the notes, so we all see what we talk about. Okay. No, I don't want to end the meeting. I want to end the sharing. This guy, and I will go say here. I guess we are talking about here, right?
Yes.
Okay. So these CNs are here. So this is the time where this is true for any time, and these CNs, of course, are functions of time. Okay. So in this case, we are looking at this probability here, which is the time t, and I'm expanding this. Okay. Sorry, you're right. My bad. My bad. I said something stupid. So please, 1 second. Yeah, no, it's correct. It looks correct to me. So if I were to write this explicitly, I would say, why don't I write this in the following way so I know exactly what I'm doing? And then I'm saying, fine. Oh, no, you have not seen me. 1 second. I have to stop share here, begin share here. So okay, so one thing I can do here, this is p yt e to the negative b half ux. I can write this as a position representation of my state psi of t, and then I'm putting here the resolution of the identity. So basically what do I do? Okay, so basically what do I do here is that this is y, by the way, not x, y. So basically what I'm doing here, I'm expanding this into Fourier states with time-dependent coefficients
where these are the eigenstates of the Fokker-Planck operator. And the way I do that, okay, do you understand this expression, right? Going from here to here, right? Veronica, where
It's not so clear.
if not, it's not so clear. Okay, so you know the concept of Fourier composition of a function in a generic basis of function. So basically, I have a function of space, for instance, L2. I have a function in my functional space, in this case, it's psi y of t, right? And I have a set that is a complete set for this Hilbert space, phi n, okay? Yes or no?
Yes.
So what I can always do, I take the inner product between psi y at t and phi n of y. And this is the instantaneous projection of my function into any elements of this space, right?
Okay, yes.
So it's like having a vector that goes around, right, in time. And at any time, I project it onto a basis, right? I do the inner product with x, I do the inner product with y. I do the inner product with x, and I do the inner product with y. So the only difference is that I'm doing this in the functional space. So my coefficients depend on time and are defined by the inner product of my space, in which case would be take the product with phi n of x of my function psi of x and t, right? That's my inner product definition. Now, this is in the simplest case in which you have the inner product for the Hermitian case. Now, if you do this, and instead of doing this, when you build your inner product, you can always use exactly when you work with the Fokker-Planck dynamics and irreversible process, you can do exactly the same thing. But now you project on the right eigenstates, but your coefficients are the projections onto the left eigenstates because of the structure of the inner product. Or if you want, you can go from one to another with the usual e to the minus beta u, right? So this secant n of t are the inner product between L on n and my p y of t, if you want. Okay?
Okay.
Did I answer?
Yes, thank you.
Okay. Other questions?
Actually, I wanted to point out the fact that in the 5.1 definition, the pi factor in the integral is evaluated at the x configuration.
5.1.
Yep.
Which chapter?
The spectral methods, today's lecture.
Are you already looking at the spectral method? Okay, 5.1. Okay, so what is the problem?
The 1 over pi of x within this z integration.
Okay, it's
you have
not, it is
defined
easy.
Is that a typo? Okay.
Okay, it's just a typo. Okay, yes. And also there's another typo here, see this parenthesis. As a matter of fact, thank you for pointing this out. I finished writing this note this morning. And so I was not able to fish all the typos. So let me go and correct this as I speak. So I put a Z here and I put this out. Let's see if this works with me. Yeah, I will upload this. It's likely there will be some residual typos here and there, but hopefully we'll fix them. Okay, other questions? Ok, guys. I guess penso che ci siamo dati da fare abbastanza per oggi. E ci vediamo giovedì, va bene?
Guarda,
Grazie, arrivederci.
A giovedì.